Hey everyone, welcome back to Calc class online here, I guess. Um, this first section in chapter 6 covers a lot of different hodgepodge of things that some of which we've actually talked about before, but I want to go through and just sort of make official. We've talked about them sort of informally in the past. I want you to see how you can sort of more formally talk about some of these things in case they come up on the AP test. So I broke this into two videos because there is so much stuff in this section, and it's not all totally related. But this particular video, this first one's going to start with these last two objectives here. So we're going to use derivative values to determine if a left endpoint or a right endpoint estimate for area under a curve will give an under or over estimate. Hopefully that sounds a little bit familiar to you. We'll go into more detail here shortly. And we're going to be talking about how to use derivative values to determine if a tangent line approximation will give an under or an over estimate. So for both of these things, I'm going to start off by just drawing every single possibility of first derivative being positive or negative and second derivative being positive or negative that there is. So there's four total possibilities. If your first derivative is positive, that means the parent graph is increasing. And if the second derivative is positive, that means it's concave up. It's opening up like a cup. So if I'm going to draw a function that is increasing and concave up, I would want a function that looks something like that. So this would be the parent function g. In the next example, we have a first derivative that's positive, which means the parent graph is again increasing, and a second derivative that's negative, which means the graph is concave down. It'll open down like a frown. So if you have a function that is increasing but opening downward, you would have perhaps something like that. Next, we have a negative first derivative, so that means the parent graph is decreasing. And a positive second derivative means, once again, the graph is concave up. So decreasing but concave up, would look something like that. And finally, this function would be decreasing and concave down. So we'd have something perhaps like that. Then in the next couple of questions, we're going to fill in these blanks. It says, below each graph, write down whether a tangent line approximation would yield an over or under estimate. So if I were going to draw a tangent line in on this graph, here's where the point of tangency occurs. My tangent line values are always below the true values of the graph. So that means I would get an under estimate in this situation. Whereas in the next case, there's my point of tangency. My tangent line will always give an over estimate for the actual value of the curve. Here we're back to being under. And here we're back to being over. Then it says, below each graph, write down whether a left endpoint approximation for area would yield an under or an over estimate. So here's my x-axis. My graph is above the x-axis. If I were to draw in a rectangle, a series of rectangles to estimate the area, but starting at the left endpoints, you can see my rectangles would all be confined within the region that the curve is carving out. I would have inscribed rectangles, so I would have an underestimate. The true area below this curve would be a little bit more than the area of these actual rectangles that I'm using to approximate it. Same thing in the next situation. If I drew in a bunch of left endpoint rectangles here, you can see there is a good deal of area in between the top of the rectangles and the actual curve. So this is an underestimate as well. Whereas when I get over here, if I drew a left endpoint rectangle, now I'm overhanging outside the function, so the area of my rectangles would be an overestimate for the area of the curve confined by the function. So this is an overestimate, and I think we're going to find the same thing here. Oops. This would be an overestimate for area as well. So let's see, what is it that causes an underestimate versus an overestimate for the tangent line? In this underestimate, G is increasing and concave up. In this underestimate, G is decreasing, but it's still concave up. Similarly, in our overestimate cases, G is concave down in both of those cases. So it is the concavity of the function that determines whether or not your tangent line is an over or an underestimate. So to put this into words, a tangent line approximation for f at some point, at some x value, will be an underestimate. So it'll be under the actual f of c if f is concave, let's see, under goes with concave up at that point. Or put it another way, if f double prime of c is positive. And then below that, it talks about area under a curve, or left endpoint approximations. Well, the left endpoint approximation was under here, which was when G was increasing and G was concave up. At this underestimate, G was increasing and it was concave, G was concave down. So that means the left endpoint approximation, the left endpoint approximation for the area under the curve will be an underestimate if it will be under the actual area if f is concave, in these two first cases, the underestimates, the thing they had in common was that the graph was increasing. So if f is increasing on the interval, or to put it another way, if f prime is positive on A to B. You can see at the bottom of the paper, then they ask you, well, what if you change the tangent line situation to a secant line situation? So like in this first example, we can see that the tangent line is clearly going to be an underestimate. But if you made a secant line, yeah, maybe you have an underestimate if you're over here. Here, the secant line is below the actual value of the curve. But if you were between the points of tangency, you would be above the value of the curve. And it would be vice versa in a situation with a concave down graph here. Here, if you were between the points of tangency, you would be below the curve. If you were above the point of, if you were between the points of secancy, is that a thing? No, it is now. If you were between the secant points, you would be below the curve, whereas if you were outside the secant points, you would be above the curve. So to answer the bottom question, if you change the tangent line situation to a secant line, would there be a change in the conclusion? Yes, if the point, let's say we're inside the interval formed by the secant points. So if you were inside that, I don't know, interval of sequency, I feel like that's not a word, but you understand what I'm saying, I hope. If you were in between the region where the line intersects the graph, your answer would be the opposite as you would have with the tangent line. Now, the reason I'm making such a big stink out of all this is because on the AP test, it seems like they very frequently ask these kind of questions. Would this estimate be an underestimate or an overestimate? And it'll either be a right endpoint rectangle for area or a left endpoint rectangle for area or a tangent line approximation. So I, frankly, to this day, as many times as I've done these problems, I don't remember very well what gives you what result. But here's what I do remember, and here's what I'm hoping you'll take out of this. You know it's either going to be f prime, the increasing or decreasing quality of the graph, or f double prime, the concavity of the graph, that dictates what your answer is. So what I would do is I would just draw each of the 4 possible situations. Like if you don't remember, I mean, you could draw a circle and then cut it into pieces. You've got increasing concave down, decreasing concave down, you've got decreasing concave up, and increasing concave up. You've got every possible situation. I like to draw them separately like this. That way everything is above the x-axis and things are consistent. But if they're asking you about a tangent line, you can kind of recreate this really quickly. You can draw in the tangent lines and be like, okay, under and under. What do they have in common? Oh, it's the concavity that they have in common. So tangent lines are dictated by concavity. Or if you have to do like a right endpoint, right? Let's say they give you a right endpoint situation. So I would just draw each of these 4 possibilities and then draw in some right endpoint rectangles. Oh, this one's over. If I draw this one in, oh, this one's under. If I draw this one in, oh, this one's over too. So the 2 things that are over, what do they have in common? Well, they are both increasing. So then I know increasing functions have right endpoint situations that give you an overestimate. You can recreate this very quickly as long as you remember there's only 4 combinations of f prime and f double prime, and it's one of those things that's going to dictate if you have an over or an underestimate, regardless of which one it is, tangent line or area, that you're trying to figure out. So here we're going to look at an old AP question that deals with at least part of this concept, a couple of them. We've got a graph here. It says that's twice differentiable, which just means that f prime is defined and f double prime is defined at all x. It says the table above shows certain values of f on the interval 2 to 13. Now what they're telling us here, f prime of 5 is 3, f double prime is negative. So we know that f is concave down. That's what that means. Everywhere, at least from 5 to 8. So they're saying use the tangent line at the point x is 5 to show that f of 7 can't be any more than 4. I'm going to quick draw a sketch of what's going on here. This is sort of a last known whereabouts problem. We're starting off with x equals 5. When x equals 5, going to the parent function, we know we have a height of negative 2. So I'm going to plot the point 5, negative 2. I know that this is for sure a point on the graph of f. Now I need to figure out what f of 7 is. I should say what f of 7 should be close to. My last known whereabouts is negative 2. That's the y value that I'm sure of. I'm going to add to that y value the slope of the graph times the length of time that I'm accumulating that slope, or that I'm counting off that slope. So if I just went right from this point, I know the slope at this point is 3. So what I'm going to do is I'm going to count up 1, 2, 3, and over 1. And I'm going to plot a point there. That takes me to approximation for f of 6. I need to get to f of 7. That's what they're asking me to figure out. So I'm going to go up another 1, 2, 3, and over 1 more. And from that, I can say that f of 7, a reasonable approximation would be 4. Now, if you don't want to graph it out, or if they just give you two x values that are super far apart and it's a pain in the neck to graph it out, well, what you can do then is you can just still start with that -2. Start with that y value that you last knew about and add on to it the width of the interval, which in our case is 2 units. We go from 5 to 7, times the rate or the slope at which you're increasing. That's what we really did here. We went up 3 over 1 twice. Oops. So we'd end up with -2 as a starting point, and then for 2 units we went up at a rate of 3, which is a total of up 6, and ended up at 4 for our final destination. Now, I've just been explaining this, or trying to explain it, just to give you kind of a backstory. But all you'd really need to do to prove it to the nice people who are grading your AP test is show this, and then just make some reference to the fact that since f double prime at 5 is negative, which they've told us in their own words, f of 7 can't be greater than 4. And we've shown that 4 is the target y value here. Since our graph is concave down, we can't be getting above that target value. Or to draw it in pictures, since our graph is concave down, let me try that again. Since our graph is concave down, and we know this point exists, we have a slope of 3. Our slope is going to be chilling out, because if f double prime is negative, that means f prime is decreasing. So this 3 isn't going to be a 3 anymore by the time you get to this point. Now, we've given it the benefit of the doubt. We've said, yeah, let's pretend it's 3 all the way through. That means we'd get to a height of 4 eventually. But being concave down, having a negative second derivative, means that that slope isn't even maintaining 3. You're actually going to end up being less than it. Then it says, use the secant line for the graph of f on the interval 5 to 8 to show that f of 7 has to be more than 1 1/3. So once again, I'm going to go back to a picture here. Here's what we know for sure. We know the graph is going through 5, -2. And now we even know, because we're going all the way out to 8, we know the graph goes through 8, 3. And we know the graph is, again, concave down. They gave that to us. So I'm going to draw a concave down graph connecting those points. Now, if I drew a secant line through here, the question kind of becomes, what would the slope of that secant line be? That's just the average rate of change of the graph between these 2 points. So that's rise over run. Your rise comes from your y values. The rise is the y's. I'm going to subtract the y values. 3 minus -2. I'm going to subtract the x values. 8 minus 5. I get 5/3. So the slope of this curve, on average on that interval, is 5 over 3. I know for a fact f of 8 is 3. That's given to us in this situation. So then wouldn't f of 7 have to be that y value minus 5/3, because you're backtracking. You're going to have to get to this, whatever this is, you would have to drop one and run backwards. So that means you're subtracting the slope off of the y value. And you're only going 1 unit, so you only have to do it 1 time. Well, 3 minus 5/3 is like 9/3 minus 5/3, because 3 is, in fact, 9/3. That would give you 4/3 as a result. That means if this curve followed this secant line, you would end up at 4/3. But this curve, we know, doesn't follow the secant line. This curve is concave down, which means it's actually going to be above the secant line. So when they say the actual value of f of 7 has to be more than that 4/3, that's true because we can say f of 7 has to be more than that because the graph is concave up. But we're not going to say that because the graph is concave up. We're going to say because f double prime of whatever, 2, or heck, you could just say f double prime is positive on the interval 5 to 8. And we've shown the algebra that concludes that 4/3 would be the absolute least you could have. In fact, it couldn't even be 4/3, because if your graph is truly concave up the whole time, it couldn't follow this line, because lines don't have concavity. All right, last one for today. I don't have the year that I stole this from, but this is clearly an AP question. They give you select values from a function here that represents the rate of change in temperature. No, it represents the actual temperature, and we're going to kind of figure out the rate of change. They do give you an initial condition. It's in the table that at 0 minutes the water has a 55-degree temperature. And then they tell you that over the course of this table, the average temperature of the water is given by this function. This is simply, notice, average value of the temperature. Temperature is the parent function here, so of course the average value of it is integral over interval. Now I would normally write this as over 20. They put it as 1/20th times this. Everyone else in the world will write it that way, but I just like the mnemonic device of integral over interval. You are finding the average value of function w then. But you didn't even have to know that for this problem. They just told you. That was nice, I guess. It says to use a left Riemann sum with 4 subintervals. 4 subintervals makes sense because there are 4 intervals you could draw from the data in the table. And whenever you see them say indicated by the data in the table, that is a red flag, and that means the rectangles are probably not going to be of equal width. They're going to be of whatever numbers we decided to give you. So if it says rectangles of equal width in the problem, you'll probably notice that these delta x's will all be the same. Here you have a 4, you have a 5, you have a 6, you have a 5. When they say this phrase, indicated by data in the table, that's what they're driving at. It's a heads up. Don't assume that just because this one's 4 that they're all going to be 4. All right, so to get the area of these rectangles, you don't even need calculus. Area of a rectangle is simply base times height. The base of this rectangle is 4. The height will be given by the left side of the rectangle. That's 55. The rectangle's width or base for the next one is 5. And then we will use the left height, 57.1, for the height of the rectangle. Next rectangle is 6 wide, and we'll call it 61.8 units high. Again, the reason I'm using these numbers is because they specifically said to use a left Riemann sum. So I'm using the starting y value on each rectangle. Last rectangle is 5 units wide and 67.9 units high. This must have been a calculator question because I don't think they would want you to waste time grinding this algebra or this arithmetic out by hand. So I'm just going to grab a calculator, I'm going to hit pause, and when I hit unpause, the number that I got will be on here. Go ahead and hit pause as well and see if you come up with the same number that I come up with right now. So I got 1215.8. I didn't divide that by 20 yet, though, I just realized. I just did the this much at the arithmetic. So if I do 1/20th of that, I would get about 60.8, 60.79, I guess. They don't ask you for a label here, which I find interesting. It's worth talking about what that would be, though. Since we're finding the average value of the parent function, the label will be the same as the label of the parent function. And the label of the parent function is degrees Fahrenheit. I'm going to put that in there because most of the time that's what they ask you. Which also kind of makes sense. Just looking at the y values here, 60.79 seems like a pretty realistic expectation for what you'd have for an average. Finally, it says, does this approximation overestimate or underestimate the average temperature of the water in these 20 minutes? Well, we know that the function is strictly increasing, which is consistent with the y values that we see here. So if we have something that is strictly increasing, that means the first derivative is positive. That means I either have this or I have this. In either event, I used left endpoint approximations. In either event, a left endpoint rectangle will be an underestimate of the true area under the curve. So I can say this is an underestimate of the actual value of this because W is increasing. Or you could alternately say because W prime is greater than 0. Since they use the phrase W is increasing in their setup, I just threw it back at them. But that's the gist. So, I will put a video out for the rest of these notes separately from this one. If you wanted to start the assignment that goes with this, you can jump ahead to number 6 and number 7 on the assignment. They follow along with what we've done in these notes. The next video will be good notes for problems 1 through 5.